Okay, we start the next example with evaluating the integral from 0 to 3 of e to the 2x with respect to x. So we start off as we have done in the past. First, we need to know an indefinite integral. Now, whenever we have e to a power we're integrating, remember we make a substitution so that we replace the power with a u. And then we calculate du from that, and du, of course, is 2 times dx. That is, du is the derivative of 2x times dx. Okay? And then we can imagine, see, what we'll end up with over here then is an integral of e to the u, but we have a dx. And so we've got to replace the dx, and so we look for dx, there it is. So we solve for dx by multiplying both sides by 1/2. So we end up with 1/2 du is what dx is. So what we're doing then, remember, is we're replacing this with 1/2 du. And as soon as we do that, we'll recognize that we can factor out that 1/2, won't we? So we'll have a 1/2 times the integral of e to the u, and the du will still be there. Now, we know how to integrate e to the u. E to the u is with respect to u. The integral of e to the u is just e to the u. Now, normally, again, we put our constant of integration, but because this is getting ready to be used for a definite integral, that constant integration is just going to subtract out, so we don't even put it in. And of course, now we go back and replace our u with 2x, so we get 1/2 times e to the power 2x. Now we're ready to do our calculations. The definite integral from 0 to 3 of e to the 2x with respect to x is our function 1/2 e to the 2x evaluated from the lower number 0 to the upper number 3, which simply means, remember, we put the upper number in first for x. So we have 1/2 times e to the power 2 times our x value, which is 3. And then we subtract what we get when we put our x value of 0 in. So we'll have 1/2 times e to the power 2 times, instead of x, a 0 value. Now, as we simplify this, in the beginning, let's see, this is 1/2 times 2 times 3 is 6, so this is e to the 6th power, isn't it? And over here we have minus 1/2 times e to a power. Well, 2 times 0 is 0, so that becomes a e to the 0 power. But remember, e to the 0 is 1, isn't it? So over on this, pardon me, in this position, we just have 1/2 times 1, or just a 1/2. So this ends up being 1/2 times e to the 6th minus just 1/2. Now, we might leave our answer that way. We might also notice that 1/2 is a common factor, and so we might factor it out, and so we could leave our answer looking like this. This is the exact value. Now, it may be that we are asked to give a decimal approximation to it, so we'd have to get our calculator out to do that, wouldn't we? Just pay attention to what my math lab is asking you to do. But if we used our calculator here, we would get the number 201.2143967, and it would depend on what level of accuracy we're supposed to round to. If we're rounding to 2 decimal places to the right of the decimal, or 3, or whatever, we would round appropriately. So just keep in mind that we might be asked to use our calculator to approximate. Okay, on the next page we'll look at example 5. Okay, example 5, we're to integrate from 1 to 3, 2 over x with respect to x. Now, of course, one of the issues that we're running into here is that we have a lot of numeric crunching, but we have to recognize the indefinite integrals that we're going to need to use. And sometimes that's real easy for us to do, and we can almost do in our head. Sometimes we need to spend the time, like we have been doing, and go through the process very meticulously to find that indefinite integral. Now, to make this problem a little easier, it's useful to recognize that 2 over x is nothing more than 2 times 1 over x. So that's really the indefinite integral we're looking for. And of course, a constant factor of 2 can be factored outside the integration sign. And so when we see that, we recognize, oh, this is one of those special integrals I'm supposed to remember. The integral of 1 over x is just natural log absolute value of x. So we have the 2, and the integral of 1 over x, like I said, is natural log of absolute value of x, isn't it? And normally we would put the plus c, but we're getting ready to use this in a definite integral. Okay, so now we're prepared to calculate with the definite integral. We're integrating from 1 to 3, 2 over x with respect to x. The indefinite integral is 2 times natural log of absolute value of x. And so that is what we're evaluating from 1 to 3. So that means first we put a value of 3 in for x. So that will be 2 times natural log absolute value of 3. And then we subtract, and we put a value of 1 in for x. So it would be natural log absolute value of 1. Okay? 2 times that. Now, there are some things that you need to remember. And, well, let's take one more step. These absolute values really aren't necessary, are they? This is really 2 times natural log. Absolute value of 3 is just 3. So let me write it that way, but we don't really need, the absolute value has been applied. And the same thing with the absolute value 1, that's just 1. Now, I hope that you would remember that the logarithm, whether it's natural logarithm or not, the logarithm of 1 is always 0. See, the logarithm of 1 base, say, 3 is 0, because remember that 0 is an exponent on the base. And if we put an exponent on any base, we get a 1 result. And of course here we understand that the base is actually e. And e to the 0 is 1. That's the reason we know the natural log of 1 is 0. So this simplifies a little bit, because in the second position we have minus 2 times a 0, which of course is just 0. And so the final answer is 2 times the natural log of 3. If we were asked to approximate it, we could with our calculator, but most likely this would be the answer that we're asked to leave. Well, again, we continue with another example or two on the following pages. So let's go to the next page for example 6. Well, as you can read our next integral here, and then the problem is what we're integrating in this case, because it's kind of a messy situation, isn't it? But we always start these out the same. If we can't do the indefinite integral in our head, then we go to the process, writing it down and going through each of the steps. Now, this is one of those complicated indefinite integrals that we need to use this technique of substitution. And we saw when we were doing the technique in the last section, if we saw square roots or cube roots, we can think of that as powers. So we can think of having x squared plus 5 to a power of 1/2 in the denominator. And whenever we have powers, it makes us think of substitution, doesn't it? So if we were to replace x squared plus 5 with a u, now to know whether this is going to be a successful substitution, we calculate du. And du would be the derivative of x squared plus 5 times a dx. And the derivative of x squared plus 5 is 2x, and so times a dx would be 2x dx. Now, to recognize that this is going to be a successful substitution, we're noticing the x that we have here, and over here we kind of have an extra x outside of that square root, don't we? And it's that matching of we have x to the first power in both of those places that tells us we will be successful. So as we proceed here and do our substitution, this ends up being the integral of x over the square root of u dx. And then we rewrite this a bit so that this is we think of this as 1 over the square root of u times the x dx. X times that fraction is x over the square root of u. And so now we're getting to the idea that we need to replace this x dx, and we can go over to the side and figure out that x dx is really a 1/2 du, can't we? See, that's really 1/2 du. Look over here. Multiply on both sides what by 1/2. 1/2 times 2x dx is x dx, isn't it? So we go through this process again, and remember that when we put that 1/2 du in there, we're going to factor the 1/2 all the way out, and we're going to be left with the integral of 1 over the square root of u du. Okay. Now that still looks bad, except we remember that the square root of u is u to the 1/2. And so when we have that square root of u in the denominator, this is really u to the power negative 1/2, isn't it? And I kind of skipped a step there, but we ought to recognize that at our level now. So we have this 1/2 in front, and we're going to integrate u to the negative 1/2 with respect to u, so we've got to increase the power by 1. And when we do, negative 1/2 plus 1 is positive 1/2. So we want to have a 1/2 factor here, exponent. But remember, we have to multiply, this is the original 1/2. We have to include a factor that's the reciprocal of the new exponent. And the reciprocal of 1/2, of course, is 2 over 1, or 2. So 1/2 times that 2 in front just gives a 1. And so we have u to the 1/2, which is x squared plus 5 to the 1/2, which is nothing more than the square root of x squared plus 5. So we've done the hard work here. Now the rest of it is a matter of just doing some numeric calculations. The definite integral from 0 to 2 of x over the square root of x squared plus 5 is the indefinite integral evaluated, isn't it? See, it's the square root of x squared plus 5 evaluated from 0 to 2. So what does that tell us that we do? We first put a 2 in for x, so that would end up being 2 squared plus 5, and then we subtract what we get when we put a 0 in for x. So that would be 0 squared plus 5. And we can see then that 2 squared, of course, is 4, so this is the square root of 9 minus the square root of 5. And, of course, the square root of 9 is 3, and we can't resolve the square root of 5. Unless we were asked to approximate, this is the result that we would leave. Well, I'm going to end this part with example 6, because what we're going to do next from this section, we're going to actually start calculating using this definite integral more than just an exercise in calculating a number. We're going to find out that under certain circumstances we can use this definite integral to actually find the area of irregular shaped regions. And so that's where we'll pick up in the next part. So that ends here for these definite integrals.